share my screen.
Alrighty, well, welcome to the Western Automation Monday morning technical class, April 21st. And we have a 2-week class starting today with our resident motion control expert, Eric Hodges. And I'm looking forward to being a student for the next couple weeks. Eric is about as good as it gets in the business, and that's all I need to say about that. Eric, thank you very much for presenting, and it's all yours.
Yeah, thanks. I wanted to start out by talking about some of the components of a motion control system, but we're going to talk about drives today, and we're going to come at it from a fairly low level and rise up into it. And then, in future training sessions, we can get a little more of a deep dive if people want to get a little more technical, but I'm going to try to keep this at a fairly base level and introduce some theory and some function, and but always talking about an entire motion control system. So I've been around a little while, as Pierce mentioned. Started in the industry in the late 90s, and spent my time as an applications engineer for a couple, 2 or 3 years, and then moved into sales and sales management roles, but always with a technical interest and a hands-on interest. So I really enjoy, helping customers solve problems. And so reach out to me anytime, anything that you need. If I don't have an answer for you, I can point you in a direction, or certainly help you to get some answers. So what we'll do is we'll talk about today. I'm really going to try to talk about drives, but you can't really talk about drives without mentioning and discussing the things that surround that drive. So we'll talk about the drive itself, how it works, and then how it fits into a complete automation and motion control system. So I like to at least talk about terminology as well. So a servo drive is oftentimes called an amplifier, and we mix and match those terms, but the amplifier basically takes a low-level signal or a command from a controller and amplifies it by controlling voltage, current, and power to control a motor or an actuator. A motor, linear motor, rotary motor, and so they're, it's a crucial role in automation of automated equipment. I used to tell people who asked me what I did for a living, I work with automated machinery, or I switched that over to saying I work in a robotics field, because really an automated machine is a robot, right? Just takes a different form. So, the servo drive is critical to that automated machine or that robotic device. And they're precise, and they allow us to control speed, torque, and position accurately, very accurately. So we'll throw some components out that are in a servo system. We'll talk about the whole motion control system a little bit, and then I'll get into a little bit about how the drives actually function. There's some interesting terminology that people use. I'll talk a little bit about that, and then some key features and functions that relate to a closed loop servo system. Talk about some applications, and then a little bit about where things are going. That's a constant change, especially at this time in our lives. Technology is advancing very quickly. So let's talk about a motion control system. And the servo drive is the power device inside that system. Converting the command, as we mentioned earlier, into a voltage and current, which results in a torque, which results in a speed, which can be controlled to a position. So that's how things fold out. And I just went from right to left inside of a loop that I'll show you later. But the motion control system, the brains of the automation system, we call that the controller. And that could be a multi-axis controller controlling, many drives and motors. It can also be a single axis. And we'll talk about, we'll do a breakout on controllers at another session. Yeah, axis and a half. You know, the servo drive, like I said, is the voltage and current regulator. And the motor, again, can be rotary, can be linear, can be brush or brushless. That's the prime mover that the servo drive is controlling, and it uses a feedback device that's either mounted on the motor, we'll say first mounted on the motor, and closely coupled to the shaft. And then there are additional encoders that can be in the system as well. So you can have an encoder on the motor, you can have a load encoder beyond the mechanical transmission, showing you exactly what is going on, maybe at the tool or further down at the instrument, for instance. And those feedback devices come in a lot of different flavors. We'll talk a little bit about that as well. And so, you know, the summary is you've got the controller commanding the drive, which produces voltage and current to the motor. The feedback device reports back in real time, you know, the motion, and the controller makes decisions on that. So, couple different ways to do things. Position feedback is the key here, and if you notice in the first graph, you know, the drive is inside, you know, the main box, and the motor has a feedback device on it. That's the encoder. Could be a resolver, but typically these are encoders in our world today. And that encoder is feeding back to the motion control. And the drive and motion control are commanded by, you know, an HMI, a PLC, some type of human interface. And the motion control gives commands to the drive. The drive, again, amplifies that into power and direction, current, polarity, and then the feedback device feeds back to the motion controller. So that's a method. And notice in the bottom section, we have the feedback device, the encoder, feeding back to the drive. So two different methods. In some systems, you'll take the feedback directly to the motion controller. It's more common to see these in early motion control systems and analog commands, or a controller that was giving a discrete signal to the drive. And I'll show you a diagram of that in a moment. But the feedback device going to the motion controller, where the motion controller is controlling the drive, and the feedback device could go to the drive. And the key here, though, is, you know, everything has the same common control method. There's a command, there's an encoder or feedback device that comes back, goes into a summing junction, and you compare the command to the actual, and that produces an error. And that error is pumped out to the amplifier to correct the error. And that is the entire servo system. So a couple different methods for controlling a drive. You know, this is your motion controller feeding multiple drives with a discrete signal. So each of these commands going to the drive. Looks like my arrow is a little out of place here. But, you know, this signal method here determines some of the capability of your system. But in this case, you've got a signal going from the motion controller to each drive. That's typically shown as an analog command signal, plus minus 10 volts, commanding the drive in either a torque mode or commanding a velocity. And you could also command position, but the most two common scenarios are torque or velocity. And then the drive closes the loop on those internally with a feedback device. And then there would typically be another encoder somewhere going back to the motion controller as well. I'm not showing that here, but for general purposes, you've got a discrete step and direction or an analog command going to the drive, and the drive is controlling the feedback. Now, this is a more common method we're seeing today. This would be a network connection. This could be Ethernet, it could be EtherCAT, it could be CAN bus, but you have a network connection going to the drive, at which point the controller can access the feedback device on the motor, get that back and forth, and you can talk to multiple drives off of one network connection. That's more common today. But knowing whether you have a discrete situation, let's say you're selling a drive and motor into an existing motion control application, you need to know what that controller is providing so that the drive can interface correctly. So closed loop. So when we're talking about servo, we're really talking about closed loop. And to me, we call it a servo motor, but servo system, it's really a servo system. So we're taking a command, we're applying a command to the motor to correct error from the actual position. What's the set point? What's the actual? Let's make a correction in between the two. So the drive, again, is just amplifying that into a voltage and current and creating a torque in the motor. Now, closed loop systems are extremely accurate. So notice this velocity regulation number here. This is one that people throw out. I mean, you could debate this number, 0.05% regulation. There are more accurate systems and less accurate systems, but the bottom line is closing the loop gives you very precise control of the shaft of the motor in both velocity and in position. And you have full torque at zero speed. So you do not have to rotate the motor to have full torque. If you see an error, you can apply current, and the drive will allow you to run 100% of its continuous rating at zero speed. One of the keys of the closed loop servo system is its ability to reject disturbances. So, you're rotating, let's say you're rotating at a constant velocity, and you run into friction and you run into a load, you start to do some work, and now you need more power. So that disturbance into the system, the drive will, again, read the actual position as opposed to the commanded and make a correction. So it'll apply torque or current to correct that disturbance. And an open loop system cannot do that because it's not monitoring real time what's going on in the system. The dynamic response, sometimes we talk to people about bandwidth. What's the bandwidth of the drive? And that's the ability of the drive to respond or make rapid changes. So starting and stopping quickly over and over again, rapid accelerations. So again, closed loop systems, very accurate. They assist in creating immunity to disturbances or changing load factors in the system. The drive is at the center of that. So not to get too deep into servo loops, that's a discussion that you could have for days, but the bottom line is that the basic systems have a commanded position on the outer loop. The position loop commands velocity. So if you're out of position and you need to speed the motor up to get back into position or slow the motor down, to maintain that proper position, it'll command velocity. That velocity loop commands current. And so you work from the right side back. So a servo amplifier that is doing all of the loop control, setting the behavior and the responsiveness to error. There are really three loops operating if you're in a positioning system. So the inner loop is your current. So you're commanding a current, and then you have a current sensor inside the motor. That current sensor feeds back to the drive. And the drive looks at two windings typically. It assumes the third winding, and it derives that one. But basically, it controls the current in all three phases of the motor if it's a three-phase brushless motor, which is the most common. Monitors that current, commands the correction to the actual and the commanded current. It sums those, creates the error, and adds torque to the motor in a direction. So at the same time, that feedback device, that encoder or the feedback device on the motor feeds back an actual velocity. And then the velocity loop will look at that, look at the commanded velocity, look at the actual, it'll command current through the current loop. And then you wrap around that a position loop that is monitoring position. So these three loops create a very robust position control system that can command position, so you can move from point A to point B, or you can command velocity with the position loop, which keeps the system tightly controlled. So this is a common method of control. I'm showing you a nested loop system here. It's just one method, but it is one that we use often. So how does a drive work? So your drive basically, as we mentioned prior, is taking a low voltage or low level signal from a controller. Could be analog plus minus 10 command, could be step and direction, could be a network command. And let's say we're sending out a command over a network, a CAN bus or an Ethercat network, and we're telling the drive constantly what the command is. The drive takes the DC voltage, and this is where terminology is always interesting. You know, I have an AC servo motor. I have a DC servo motor. Those two things get intermixed a lot, but the bottom line is your drive is operating off of a DC bus. If it has an AC input, let's say it's 110 volt single phase AC voltage going to the drive, we'll commonly refer to that as an AC servo motor. But in effect, we're taking that AC voltage into a rectified front end, a rectifier, and we're rectifying it into a DC voltage. So a 110 or 120 volt AC signal gets rectified to a DC. Typically, that'll be about 165 volts, and it's 1.414 times your AC voltage gives you your DC voltage. And so 165 volt DC bus is what your motor will be operating on. And we get it into a DC bus so that we can control both the polarity and the level of current that's flowing from that power supply. So you can have a DC bus supply direct, or you can have an AC input to your drive, but your drive is always converting it to DC, and then the transistors are going to operate off of that. So the transistors switch. Those are in the power stage of the drive, and they turn on and off, and PWM or pulse width modulate to create current in the motor. And I'll talk about that a little more. I'll show you a graph of that. But we call those IGBTs, and these power transistors are typically used for your higher voltage systems. We'll use, as noted here, MOSFETs for lower voltage DC drives, 24, 48 volt. But these devices operate in a similar fashion. So what they do is I describe it like a strobe light. Pulse width modulation allows you to, if you fire faster in short bursts, then you can create a duty cycle of current flow. And I'll show you a graph of that in a moment. But basically, we have two sets of transistors on each phase, and we can turn those on and off, allowing current to flow through the windings, and we can control the current in each winding, and we can control the polarity, the direction of flow through the winding. And that allows us to create current and the winding, which opposes or attracts the rotor of the motor's magnets. So you'll see a couple different methods of what we call commutation, and that's controlling the current in the stator of the motor and the position of the rotor, which has permanent magnets on it. I'm not going to talk deeply about trapezoidal or six-step commutation. We primarily are sinusoidal today. The technology's advanced, but you'll still hear it. You'll still see the feature in many drives that they can commutate in a trapezoidal fashion. But what you're basically doing is, in a six-step system, you have Hall sensors in the motor, and the Hall sensors are every 120 degrees. And when we compare multiple hulls and their on-off states, you can resolve down to 60 degrees. But these are the 6 states here that you see when you're using 3 Hall sensors, and they give you 6 conditions that you can see. So when you power up and look at this motor, you can see the pattern that's formed by the Halls, and you can know exactly where the rotor is relative to those. The rotor turns on those Hall sensors, and then we know where the rotor is relative to the windings on the outside, and then we can have 6 states of energizing in the windings of the motor, and we'll call those U, V, and W. And so 6 states, we can turn those on and off and sequence through those, and then the motor will rotate. And so this is an older way of controlling. Drives only had the intelligence to control these 6 states. And so the motor would rotate, but it would have a little bit of torque ripple. It would bounce a little bit as it went into these different states. And even though you would rotate them fairly quickly to get, let's say, 1800 RPM or 2000 RPM or whatever your speed is, the bumps are smaller, you get torque ripple. And then we basically moved to more intelligent controls as our processors got more and more powerful, and we started to do a sinusoidal method of current control. So I'm going to talk about sinusoidal and how it's smooth now instead of having these 6 steps, but I wanted to at least show this graph of pulse width modulation. So your variable frequency drives work this way, servo amplifiers work this way, and so we talk about the transistors, right? So these transistors that we have connected to the windings, we have a plus and a minus on our DC bus, and we can make that flow through the winding in a clockwise direction or a counterclockwise direction and create reverse polarity. And what we do, I like to describe it as a strobe light, right? But the longer you hold the transistor on, the higher the current will rise. So this is an indication. The red channel is the pulse width modulation, so turning on and off. And then we're doing it for a shorter and longer time period. So you see the large time period allows current in the blue line to rise. The shorter time period, it won't rise as high. And you can see the really short time period reduces it. So by controlling the time that you have the transistor turned on, the width, so pulse width, by controlling that time, we control the amount of current rise in the winding. And by controlling that pulse width modulation, we can create a sine wave of current with a polarity. And if you looked at this and you drew a center line horizontally, and we said that, this is a positive current, this is a negative current, this represents what is in the winding. And if we do this in all 3 windings, then we can smoothly control the current in that winding and the polarity in the winding. So now we can accurately control the torque to the shaft by controlling the current in the winding. And so what you see here is this is a DC voltage that we're controlling, but we're controlling and creating a sinusoidal current in the motor. This is the job of the drive amplifier. So what does that do for you? This is always a confusing graph for people, especially if you're learning or getting introduced to motors and coils and how motors work. There's a whole nother discussion we can have about the motor as well. But basically, I'm assuming most of you guys have a little understanding about motors. And the basics are you put current through a coil that's wrapped around a ferrous material, and you create a magnet. Run it through clockwise, depending on how the direction of the coil wrap around that ferrous metal is, but run it clockwise, get a north pole, run it counterclockwise, get a south pole. And as we change in the winding, the polarity and the strength of the current or the force of the electromagnet it opposes and pushes and pulls the permanent magnets that are attached to the rotor of the motor. So this is the PWM. I wanted to show that graph over here on the bottom right. It relates to how we're creating the current in the coil. And this is what we will call 0 to 360 degrees, or a full electrical cycle. So the drive, the servo amplifier, is creating a sinusoid. One of those electrical cycles equals the number of poles in the motor. So it's a single cycle on a pole. So in this particular image that we have here, we've got 2 poles, or 2 pole pairs. So each of these coils they're wired together, as you can see. So this is 2 pole pairs, or what we loosely call 2 poles. So one electrical cycle is half the rotation. The other electrical cycle is the full rotation of the motor. And if we control that current sinusoidally, as you're seeing in the graph here, we've got 2 electrical cycles to complete this plus minus current, and we rotate the motor. So this is what happens in variable frequency drives. It happens in servo drives. It happens in stepper drives, just slightly different ways. So here we're creating a nice smooth current, rotating the motor. And unlike the 6-step or trapezoidal commutation where you hard shift to a level 6 times, there's way smoother motion, much lower ripple, much easier on all your electronics. Soft shifting is what I like to call it. So I'll lay the 6-step over top of the, yeah, you got a question?
Yeah, Chris, here real quick. Does that also mean it does create less noise in the PW or in this setup versus in a stepper, or does it still create an equal amount of electromagnetic noise?
It's a lot smoother, less noise. Some of the noise created in steppers are natural harmonics. Some of them are vibrations occurring because of the hard stepping to each level. Steppers are a different discussion, and we can have that later, but they're unique motor construction. And 100 pole, for instance, is a common 1.8 degree stepper motor that you'll see. That's 100 poles, right? 1.8, 360 divided by 1.8. So there's a lot of little steps in a stepper, right? Microstepping is another way to subdivide that down even further. But we'll talk about steppers later. But yeah, servo is quieter, Chris. It has less vibration, therefore your natural sound of the motor is much quieter. And you can servo a stepper motor. Remember, I said servo is really a system description, not a motor description, right? But stepper motors and servo motors are definitely constructed differently. But if you just use it as a system discussion, I think it applies a little bit better. You can servo a stepper as well. We should probably do another stepper session later as another day. But so Eric, smooth motion, yeah.
Eric, on your point, you can actually servo a hydraulic or pneumatic system too, right?
Yes. Your thermostat in your house is a servo system, right? So you can servo a hydraulic system. You've got a command to an amplifier. The amplifier is moving a valve in the hydraulic case. And let's say it's a directional valve. So proportional directional valve, for instance, varies the flow and the direction of the fluid. To control an actuator, hydraulic cylinder, hydraulic motor, with an encoder or a feedback device of some sort giving feedback to the system, then you've got a closed loop system. So very, very common. And you can use servo controls in hydraulic systems. So the amplifier in this case is converting the voltage and current, where in a hydraulic system, you've got a power unit that's creating pressure and flow, and your valve is like the transistor. It's changing the amount of flow and the direction.
So voltage current pressure flow. Those are analogous in the two systems.
Absolutely, and I use that all the time, as you well know.
I got a question for you. I wonder if you can give us a commercial understanding of the relevance of trapezoidal drives versus sinusoidal drives today. It used to be that the trapezoidal drives were less cost, but
in the older trapezoidal drives, think of it as you know, a Pentium chip, you know, and an i7 chip now, or you know, the old trapezoidal, the original trapezoidal drives that changed in 6 steps the current in the motor. Those drives were not as powerful of a processor or a controller inside. They could do this with less intelligence. You can do it with very simple logic, and so they were lower cost, and viable. You do not need, you know, you do not need what you don't need, right? So they were very cost effective, very robust. And if you, but you wouldn't want to use one for scanning, for instance, where you have this torque ripple. So if you're taking an image of something, scanning something, you want really smooth motion to not disturb your camera, right? Or your line scanner, or whatever it is that's doing the scanning. So how did they overcome some of those things? Well, they would highly gear motors, for instance. They'd run them very fast, so the torque ripple was really small as compared to the, you know, get the inertia moving through that that area. But and then they would gear it so that they would shrink that ripple down even more. Today, all of your drives, as the chips got more powerful, as controllers got more powerful, signal processors got more advanced, you can still run 6-step designs, and motors can be optimized in how they're designed to operate with trapezoidal versus sinusoidal, but you can still run them. They are viable. Just all the new modern controls can do both. But if you have both and you can run a sinusoidal, why wouldn't you, right? So it's even the same can be said for brush motors. Whether you're brushless or brush, you know, most of your servo amplifier products today can run both. Slightly different control method, but you'll still see a lot of motors that you'll find, old motors that are designed for trapezoidal commutation, and you can run those with modern controls. So yes, lower cost 6-step amplifiers. Sinusoidal was more cost, but the cost of components has come down dramatically in the electronic world. And I think, Pierce, you might even see a flip now. If you try to get a trapezoidal amplifier, you might find that because they're not made in as high a volume anymore, that the cost is a little higher. I might be proven wrong on that, but for the most part, I think you're going to see more modern electronics that support sinusoidal.
So in general, then you could never go wrong replacing a trapezoidal on an older application and upgrading it to a sinusoidal. You'll just get better performance.
Better performance, yes, good point. Better performance, smoother motion on your mechanisms, longer life, quieter operation, and less surges on the mechanic or on the electrical side as well, because you're not hard stepping between pulses or 6 steps. You're smooth transition. I mean, this is, so I laid a 6-step over top here. This is a 6-step laid over top of a sinusoidal. So the 6-step, you can see 1, 2, 3, 4, 5, 6 steps, right? And let's say that this left graph is current, right? So you hard step to half an amp, then hard step to an amp, you know, step back down, and you get a pulsing effect on the motor. And sinusoidal is nice and smooth, right? Nice and smooth. And so again, you're going to see more sinusoidal today. To Pierce's point, there are trapezoidal products in the marketplace. You'll see them, and know that you can take a new modern day control, run, you know, replace that old amplifier. And just did it a couple of weeks ago with one of Chris Keller's customers. They were replacing an old CNC machine, replacing some old trapezoidal drives with modern drives, and running nicely. So these are the benefits that we talk about with sinusoidal, smooth torque, excellent low speed performance because you have fine control over the current, right? So going at slow speeds, that sinusoidal control is much smoother and much more controlled because you have a processor that is accurate, and we've got feedback at high resolution in modern days. You can really control the angle of the pole, the electromagnetic pole that is lining up with the permanent magnet on the rotor, and energy efficiency, and then we get into algorithms. How are we actually controlling the current? There's multiple ways to do that, but field-oriented control, FOC, sinusoidal, those are synonyms for each other, but these are really effective ways to control current, efficient. And if I compare the two, this is kind of a chart of the general comparisons, right? That we've talked about over and over. So where are trapezoidal and 6-step, perfect for, right? Fans and pumps, there's a no-brainer, right? You don't really care if you have a little torque ripple with a fan or a pump. It doesn't result in the output process, right? Where precision robotics, medical devices, if we're going to be scanning DNA or doing a, any kind of mapping, you want very smooth, very efficient motion. So a little comparison of open loop and closed loop systems. Servo systems are closed loop. That's the servoing that we mentioned. There are open loop systems as well, and they're very cost effective and perfect for certain applications. They don't have feedback, so the devices are very simple. You're counting on things like sizing, that you've oversized the system to be able to handle maybe a duration of mechanical wear and increasing friction and not changing the outcome, or your process is not as sensitive to small disturbances or small variations in the output. Closed loop, continuously monitoring where we're at, real time. So we always know where we're at. We're always correcting it, and we're able to do that very precisely. So, real-time feedback, accuracy. You can just think about, closing your eyes and throwing a dart, opening your eyes, seeing where it's at, closing your eyes again and throwing another dart, trying to improve upon it, or leaving your eyes open and throwing the dart, right? So open and closed loop systems, typically your closed loop systems are in more precise, more accurate motion control systems, right? And again, just another little comparison, feedback, accuracy, self-correcting, just some general characteristics of open loop and closed loop. And I like to jump right to the bottom here. Here's one where we say typical regulation, 0.01%. So this graph is better, 5 times better than the initial opening that I gave, because we now have higher performance feedback devices, higher performing controllers, higher resolution in the control or in the drive to read higher resolution encoders. So much better control if you need it. So types of servo drives. So you're going to run into this a lot. You're going to run into analog and digital. So modern day drives, pretty much everything that we work with today is a digital drive. We do have a few analog products. I can tell you I haven't sold an analog product in probably a decade. Even for replacements, I no longer go there. I tell customers who come to me, hey, I've got an analog drive. I just need to replace it. And I say, you're better off just getting a digital drive to replace it and running the analog signal to the digital drive. But it'll act like an analog. So analog would mean that the entire drive circuitry there is analog, where digital drives, everything is discrete. Integrated drives. So, you can have a drive only, although most drives today have some intelligence built into them. That is a trend that we've seen for the past 15 years or more, is drives, the processors are pretty inexpensive now. And when you use a processor to control the voltage and current in the drive, you've got overhead and you've got extra intelligence there. So it only makes sense to utilize that, right? So you can do some control typically inside your servo amplifiers now. So integrated motors and drives, and integrated drives and controllers. So we have a number of voltages. So 480 down to 9 volts DC. Each of our manufacturers plays in kind of a certain sandbox. You'll see that their products are driven towards one voltage and current range or power level than another. Where are you going to see the 9 to 180 volt products DC? A lot of 9 volts is a minimum because it's typically going to be on a mobile device, right, using a battery. So AGVs, automated guided vehicles, autonomous vehicles, things of that nature. 480, 230, more common in the industrial world. You've got power to the plant, 3-phase power or single phase, and we're using that to generate. Again, I mentioned earlier briefly 1.414 times the AC voltage. So this 480 volt drive would be 600 plus volts, 650 volt DC, 690 volts, 230. That's gonna be your 325 volt DC operating on the motor. 120 is 165 volt DC. And single phase and 3-phase, very typical. Then the other is the form factor. So we have panel drives that have an enclosure around them, shown here on the right, with connectors on the front, very common. We also have board level drives, where you have a small board level that plugs into, let's say, a connector board. We call those carrier boards typically, for ease of use. And these would be typically in instruments or in smaller machinery, right? Larger machinery where you got space, real estate's not a big deal. Maybe you use a panel drive. And then PCB level drives, where a customer is going to design their own circuit board and they're going to plug these into their circuit board. I've got a customer using 6 4-axis drives into their own circuit board, and they're all stacked up, and they get economies of scale with how they wire with their power supply, routes, connectors, etc. So analog and digital servo drives that are integrated in with a motor on the back of a motor, controllers that are integrated into the drive, and a variety of power levels. So key features now with these systems, controlling, again, position, speed, and torque. And you can do that in a drive today, standalone or with a controller. Most of your drives that are going to integrate into a control system have communication interfaces as well. And we pretty much cover the gamut now. But the fastest growing industrial motion control network today is EtherCAT. EtherCAT, Ethernet, CAN bus are the ones that you'll see the most. Modbus TCP, RS-232, 485, those are also common. Those are typically used when you have a PLC, something that isn't going to do a lot of real-time control of the servo, but it's maybe going to command the servo, hey, go make move number 9 in your menu, or move from point A to point B. And the control is simple, where the EtherCAT, CAN bus, even some of the Ethernet protocols, they're constantly monitoring what's going on with the motor and correcting, and a more sophisticated level. And we'll have another session talking about controllers. And there are a number of proprietary interfaces that are out there, where a manufacturer has created their own interface. Feedback drives support lots of encoder types. These are your most common that we see. Digital A quad B is an incremental encoder. This is by far the most common, the lowest cost, and very effective. And in the old days, we used to have 1,000-line encoders, even 500-line encoders. Today, we have 50,000-line encoders. We're etching encoders smaller and smaller, and then we're going to sine cosine, where we can interpolate that, divide those sine cosines up into small increments, millions of counts per revolution of the motor. And then we've got all of these other protocols for serial encoders, where we're requesting information back from a little bit more intelligent encoder device that can do absolute. And I would say maybe 10 years ago, I'd get 1 out of 10 customers interested in absolute feedback devices. Today, it's probably 7 out of 10. So the cost on the absolute devices has come down. Most of your drives can support, it might be maybe the next level up of drive capability, so a little bit extra cost, but you can read all of these absolute encoders and feedback devices. And then, of course, your drive is responsible in almost all of your applications. It's responsible for protection of the system. So it's responsible for overcurrent, overvoltage monitoring, temperature in many cases. If you, it'll protect itself thermally, but it also can monitor a motor-mounted thermal device. So that can be either an on-off thermostat for over temperature on a motor, or it could be an analog device, a thermocouple, a thermistor, reading back to the drive. And if it goes back to the drive, typically if your drive is a network drive where you have a high-level motion controller or a PLC that can talk to the drive, then it can actually monitor that, log it. So your drive, as it becomes more capable, offers more diagnostics and more protection to your system. And then, of course, with a digital drive, you've got custom firmware options that you can typically deploy. You can add features and capabilities to the drive without changing the hardware in many cases, just by changing the firmware and simply downloading it to the drive. And these are things that we offer in a lot of our products with OEMs who want a special feature. We can easily add that into the drives. So the digital drive allows you that extra capability. So where do we see, this is the world we all live in, right? So the industries are the ones I think are really popular for the geography that you guys are in, and the marketplace there: robotics, life sciences, aerospace, medical devices, semiconductor. You can read these. Maybe some on the right are just more examples, but maybe not as prevalent in our marketplace. But again, these are automated machines. These are robotic devices, autonomous vehicles in some cases. Think about aerospace. We're pointing gimbals and instruments at the sky, tracking devices in the sky, all closed loop feedback. So the motion control market, just a couple quick blurbs. It's large. It's growing. It's going to continue to grow. I think these market, numbers are always interesting to me. What part of it do we serve? There are many parts of this that we don't serve, but the automation robotics area is one of the top growing in the globe. So there's a big piece of that we can go capture. And you'll see more and more people updating systems from open loop to closed loop, increasing the performance of their machines and adding value. So AI and machine learning becoming more and more part of the servo drive world. So servo drives will be getting predictive maintenance capabilities built in, self-tuning and adaptive tuning, so that less and less do you have to be an expert with tuning. The AI and machine learning that is now part of many systems will start to slowly end up in our world of drives. We already do some of it, and we can talk about some of those features in a later session. But AI is going to dramatically affect our performance and our capabilities with our products over the next 5 years. IIoT, so real-time data being able to be pulled out of these digital drives is more and more on the forefront of OEMs and manufacturing facilities. They want to see real-time what's going on in their machines. How do they keep them up and running? Is there something starting to fail, and do we want to pull it offline? So digital drives give you the ability to monitor things real time. And then, of course, we're getting more and more power density with materials, and energy harvesting seems to be it's always been around, but motors and servo systems, not only do they motor, they also generate. So you can use them to capture energy as well. And then the plug that I'll throw for our products, we've got a number of manufacturers, 4 of them shown here, who manufacture servo drives. I also threw a couple other little images up to show that some of these companies manufacture other things other than drives, and drives are just part of their portfolio. Copley happens to be, call it a 6 kilowatt and below. They're actually pushing their power level. These are really OEM focused products, can run anybody's motor. Trio also has a couple drive lines, but they also have motors to go along with them. And then they're a multi-axis controller company. So they have multiple form factors and ranges, drive motors and control, so complete motion control systems. Stober is primarily our gearbox company, but they also have motor and drive technologies, a natural expansion of their gearbox products. So, very, very solid offering there. 480 volt, Copley's 230 volt and down, primarily DC. Trio is 230 volt primarily, although they have a couple options outside of that. Stober 480, 230. And then Toyo is an actuator and stage manufacturer, but they also have servo and stepper drive technology to integrate in with their product offering. So again, we've got a lot of flavors available for people. And that's pretty much it for me today. Open to any questions if you want to flip back to another slide or talk a little more deeply. But I wanted to at least kind of start with the basics today.
Well, Eric, thank you. We have a second section of this presentation coming up in 7 days with Eric. I want to point something out for you from a commercial standpoint. The entrenched market shareholders, which in this country would be companies like Allen Bradley, are at a nexus in their timeline because, as Eric said earlier, the change in technology, the rate of change is so rapid right now that some of these companies, and Allen Bradley is a good example, really haven't kept up. And they're at risk. There's a large portion of the market share right now that's going to be in flux based on the fact that more capable, less costly technology is available. The old brand name loyalties are eroding rapidly. A lot of our job is to help customers increase the value of their motion control systems. And we are uniquely equipped, both in experience and product, to help you do that. The reason we have such a broad range of products is because every opportunity has different avenues of entry, different value propositions, and we try to be as broad-based as possible to allow you to take advantage of these commercial brand changing applications. So with that, Eric, thank you very much. I've learned a lot, and we're looking forward to the second half of your presentation next week. And I've taken some notes on the things that you think we should focus on in future classes, like some stepper technology. And I will try to work those into the schedule. But with that, it's 7:58, time to go to work. I wish you all a good week. We'll see you next Monday.
Thanks, everybody.
Thank you.
Thanks.
Thank you.
Right.
Thank you, Eric.